But this would just be fun to have.
Build your own. Build your own
Yeah,
popsicle sticks.
I love
Not
that.
a physics experience.
And that's your, like,
But it's a
DIY
trebuchet.
version.
Why not
Making it a
both?
physics
You
experiment.
make your craft for more than it's worth.
You just find that and then scale it up 100.
Okay, so real quick, the one little thing I want to go through today is to close everything up. So we said
This is my last
yesterday,
problem.
told you about the white lie. So Newton's second law really should be.
F equals. Yes.
Or in non-calculus terms. So if we're not talking about variable forces, if we want to make this simple and just do this with constant forces, we could just say delta P over delta T, right? Okay, so if that's true then, we're going to take this non-calculus,
Woo! Did it.
we're going to take this non-calculus definition, accurate definition of force, then we could come up with something pretty cool out of this. We could say if we just cross multiply, this yields the relationship that change in momentum equals F delta T. Okay? So we call this quantity a change in momentum. We call this impulse. And this is a big part of when we talk about collisions. Okay, so let's take an example here. We've done a problem like this before, but if you're driving along in a car and you're traveling in the positive direction, let's say, and you're traveling at 70 miles per hour,
Can I be the opposing color?
and you put on your brakes gradually and you decelerate over a, let's say, a 10-second period of time. What's your change in momentum? Well, I mean, what's your final momentum? Zero. Your initial momentum is whatever it is, your initial mass times velocity, right? And we won't even calculate, but it's big, right? You got a car moving along at 75 miles an hour. So if you decelerate over a 10-second interval, your impulse is negative whatever you started off with. What if you decelerate over a 3-second interval? So you're slamming on the brakes and coming to a halt really quickly. Maybe 4 seconds.
Would it be 2.5 times whatever your initial momentum was?
Your change in momentum. Yeah, I can. So let me say it again. So you're starting off, same initial conditions. You're starting off traveling that way at 75 miles per hour in your car. This time you slam on the brakes and you come to a halt in 4 seconds.
The change in momentum's the same.
Same. Everybody agree? Because you end up at rest. And you started off with your initial momentum was the same, right? Okay. What if you, I don't like you to think about this one, but what if you come to rest in a fraction of a single second by slamming into a concrete barrier? What's your change in momentum then?
Same.
Same. It's the same. The impulse is the same in any of those 3 situations, right? Okay,
Wait, impulse of the change in momentum.
change in momentum, yes. The impulse is going to be the same in any of those situations, right?
That's a lot.
Does that make sense?
Yeah.
Okay, but they're obviously much, much different scenarios, right? Qualitatively, they're much, much different scenarios, right? Well, why might that be? If we look at the fact that the impulse is equal to the product of force and the time interval of the impulse, right? That tells us something important. If the time interval is big, what's that telling you about the force?
Small.
It's small, right? That make sense? If the time interval is very small, that means the force must be very big, right? Okay. And so
Is that-
if you think about the science of collisions, yeah,
And what force is that referring to? Is that force on
this
the
is,
car?
okay, so yeah, this is the force acting on the car, right? So whatever's causing the change in momentum, okay? So this simple impulse momentum equation is the impulse force equation where we define impulse in terms of force and time. That's really the physics behind collisions, right? And if you think about, let's go back to a car again. We go to cars all the time. And this is a great example of, in a car, what can we do? Obviously, cars are a mode of transportation, but cars, the biggest concern in a car is that, if things go wrong, that the occupant of the car is gonna live. We want them to be safe, and we go through a great deal of trouble to rate cars and market cars and build cars based on their safety, right?
So if a car is traveling at whatever speed, hits a barrier and stops within half a second, there's however much force applied to it.
Right.
But if there's two cars that hit each other and they stop within the same time and they're going the same speed, is it the same amount of force applied?
It would be. Absolutely, it would be. Because if the momentum is changing by the same amount, then yeah, it would be the same amount of force. And here's another way to maybe just conceptualize that. If you hit a stationary car, you're actually going to move with the car a little bit, right? So you may not come to rest as quickly, right? If you hit the concrete barrier, it's not going anywhere. You're coming to rest pretty quickly. Two identical cars hit head on, that's really the same as hitting the concrete barrier, isn't it? Right?
And then if one is going faster, and then if one is slower, slider.
Then it could change things a little.
Realistically, the math wouldn't matter whether it's two cars crashing at 70 or one car that's still and another crashing in at 140. Realistically, I don't think that math matters too much.
Say it again.
So head-on cars, it doesn't matter if they're both moving 70 in the opposite direction, or if this one's not moving at all and this one's moving 140.
Right. Right. If they're identical cars. Right. Agreed. Now, if one car is heavier than the other, you honestly would be at a little bit of an advantage in the heavy car. How come?
Because you're going to bulldoze
Right, because your change in momentum is going to be smaller, isn't it? Right? Does that make sense? The change in momentum, did everybody buy that? You're not going to change your velocity by as much. Does that make sense? You're getting smaller accelerations. If you're in the big truck that's going to slow down very slightly, that's better than being in the little car that's going to be moving in this direction, and then all of a sudden, a split second later, be moving in that direction. Right? Okay. So let's talk about the ways that automobile engineers, the guys that design the cars, what are some measures that people have taken to make it safer for the occupant? Because really the forces we're talking about that we're actually concerned about are going to be the forces acting on the occupant of the car, right? It's not so much that we care about what's going on to the car, we care about the occupant of the car, right? And those need to be sublethal. What's one thing? Okay, the big, and this is, okay, and this is the one that I really want to spend a little time on. They make what's called a crumple zone in the front of the car, right? So the hood collapses, and it's literally called a crumple zone. So you used to hear this, and a lot of people still say this, that they want to put their kid in one of those old, just great big tanks, because when they get in an accident, they don't even look like anything's happened to them, right? They look as though, maybe they have a scratch, but the frame hasn't changed, the car isn't all crumpled up. And that might seem to the person who is not as scientifically literate about things or doesn't understand the science behind it, that might naively seem like a good thing, but why is it not? Okay, the force has to go somewhere, but let's try to couch this in physics principles. What's going on in terms of the profile of the impulse there? If you're driving along in your 1957 Cadillac and you smash into a concrete barrier and the Cadillac just kind of bounces and stays there, right? It doesn't crumple.
Then you get thrown out.
Then that's a very, 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 very small change of time for the momentum to change.
Exactly. So you in the car is coming to rest almost instantly, and you got to stop somehow. And does that make sense? You've got to come to rest. So where is all that force going? best case scenario, you're wearing a seatbelt. Sure, maybe you're wearing a seatbelt, but you're still, the force acting on you is gonna be tremendously high because the time interval is short. So all that force is gonna be happening, it's gonna be focused, the pressure is gonna be tremendously high, isn't it? Because force divided by the area of that seatbelt is gonna be a really high pressure. So what's it gonna do?
With that like pressure rib cage.
It's gonna kill you, yeah, right? It's gonna, there's this large pressure pushing right on your thoracic cavity, and that's not good.
I don't think I see that.
So what are some things that we've done then? Seatbelts, turns out seatbelts are not really designed to increase the impulse. They're just designed to prevent you from being thrown out of the car.
Yeah.
Okay, so what have we done since 1953?
Added a
Crumples.
Crumple zones. Okay,
Airbags.
Cadillacs don't have that, but you could almost retrofit your Cadillac with something that would still be a lot better.
Airbag.
Airbag, right, an airbag. And when you have an airbag, then the seatbelts are designed so they do give a little bit, okay? And then why is the airbag good, obviously?
because it's kind of also soft.
It's
not like
it's
soft
its own
rock,
crumple zone for yourself.
It's its own crumple zone, right? Then that allows you to decelerate
Crumple zone for
between you and the dashboard or you and the steering wheel. It allows you to go through some deceleration phase between you and that hard object where it's smearing it out in time. And it's also spreading the force out over a larger area, right? Which is different physics, but it's still important physics, right? You want to have the pressures be low enough that it's not going to break a vital part of your body, right? So you spread it out over a large area, and that's much better. Okay, it's why you would rather get, would you rather get poked with a baseball bat or a needle sharp spear? Well, probably a baseball bat, right? Because it's got a larger area, so the pressure's a lot smaller, right? You have a tiny little area on something that's very sharp, and so it pierces because the pressure's so high, okay? So there's that part. Then there's the crumple zone part, right? Modern cars are designed so that the entire span of the hood, which is a pretty large distance, right? I mean, you're talking about 6 or 7 feet there total. That's designed so it will crumple up like an accordion, and it's got varying degrees of stiffness in the crumple zone. And so you're gonna blow through part of it pretty quickly, but then if you still haven't dissipated all the energy, momentum we can say in this case, then you're gonna hit a stiffer part of the crumple zone, stiffer, and so it ends up, it's graduated, and it ends up extending that time interval for as long as possible. What happens, just kind of this is more of an engineering aspect to this, this is just kind of a cool, it's a cool mechanism for dealing with the engine, because the engine's not gonna crumple, is it? So what happens to the engine, which is between you and the front of the car, when your car smashes like that? Where does it go? Because it's got to go somewhere. It goes down, right? The engine is designed, the drive shaft is designed to shear off, and the engine gets shunted under the car, so it crumples underneath you in an accident like that, in a well-designed car, right?
Hit something.
What
I
if
don't know
you're
if you'd end up
driving a
flipping over the.
What's
What if
that?
you're driving a Beetle?
If you're driving a Beetle, like an old Beetle?
Yeah. Well, even the new ones have the engine in the back.
Oh, yeah, that's true. Well, I mean,
Well,
if
then
you're
is
in
it
a-
just the hood in the front, and then
And then there's that empty cavity that.
And just-
well, so, right, but that's where that crumple zone's designed. So they've got the frame is designed to accordion when you hit it.
My dad has that in his truck, and he got in the pilot technique, and his car was completely messed up like that, but he came out with like no scratches.
And that's what you want. And that's the other thing. People look at cars in the after accident and they look terrible. That's what you want. You want your car to be totaled.
The
That's
cops around him didn't think that he made it, but then he came out and he was perfectly fine.
right. It looks pretty bad from the outside. So then there's one other part of this then. So you're in the part of the car that you don't want to crumple around you. Okay, and that's called the safety cage. Right? So the actual cabin of the car where the occupants sit is designed with hardened steel, it's reinforced so it doesn't crumple, just the parts around it crumple. Yep.
If the front of the car was made with a natural substance that was elastic, I don't know, where it would crumple and then.
Would
that be dangerous? Or?
I was gonna let you guys kind of discover this on your own in a future discussion, but it's such a good question, I'll answer it. It would be worse. it'd be worse.
Because not only do you have this, you also have the reporting.
Exactly. So if it's perfectly elastic, it doubles the change in momentum. So you don't want an elastic collision, you want a perfectly inelastic collision, okay? Yeah. Right, and what would be a way to understand that? If you're maybe a softball player, when you hit a softball, it's fairly elastic, it's gonna bounce off the bat, right? If you were instead to hit a beanbag or something, what you'd find is it wouldn't be such a violent impulse. It wouldn't hurt your hands as much, okay, if that makes sense. I mean, bats are well designed. If you hit it in the right spot on the bat, it's designed so it's going to, you hit the sweet spot, it's not gonna hurt your hand so much, you know, and you've got the whole weight of the bat, the large momentum of the bat that's gonna rotationally push it through. But when things bounce, yeah, that makes it worse. Yeah. Okay, what else was I gonna ask you about this?
So is that,
Okay, so going back to car safety then. So when you buy a car, it is worth the extra. When you're going to college, everyone's trying to buy a cheap car. It's all right to get a used car, but get a used car that has those safety features, because they really do save lives. And you don't buy insurance in any kind, including a car, because you think you're going to use it. But if it ever happens, it pays for itself a million times. I mean, because what's worth more than your life? You know, I mean, you have to, so it really is, it makes sense to get a car that has airbags, that's a modern car that has traction control, you know, and that's a different thing, but you know, you definitely want to have anti-lock brakes. We've talked about that before, right? You want to have, and new cars are just so much better than old cars. New cars, they actually have, you know, traction control devices where, like, if you turn sharply, the car will sense that, and it will apply pressure or apply braking force just to the right tires. So it does a quick algorithm, and it figures out, okay, what do I have to do here to keep this thing from losing control? And they actually do that stuff. I mean, so modern cars have a lot of safety features built in. You want to have airbags, and you want to have curtain airbags too on the sides. Side collisions are the worst. I mean, if you're getting hit with somebody coming at you full speed from the side, that's real bad. You don't want to put yourself in that position. You know, you got to drive defensively and avoid that. But if you get in an accident where there is some force coming from the side, having that airbag there is huge. I mean, that's about your only protection. It's either hitting the side of the car that's going to be hard, or you've got that little bit of an airbag there to smear out the collision in time a little bit, and that's all it takes. So what do you do then if you're losing control and you know you're going to crash? Where do you want to crash on the car? The front of the car. Yeah, you want to crash the front of the car. That's the best place to do it, right? And it's going to ruin your car, but so what? Insurance will pay for it, right? Okay. It's just a small class. I'm tempted to let you guys. I'll put up a couple assignments and let you just work on it a little bit. How's that? I mean, I'll put the new ones up early. Well, that's fine. Yeah, you may, or you can, if you want to work on some trebuchet design, you can work on that. The trebuchets can be pretty simple. They don't have to be anything super complex, but they do have to be well built, I think. You know.
You have to at least fire something afoot.
Mm-hmm. No, you want to be able to fire something. And you could have the debate: do I want to be able to fire something really hard, a long distance, or do I want to have something that's very repeatable for a short distance? And I'm not sure. I think repeatable for a short distance might be just as good.
more accurate?
Sure, have you ever built?
I have. In fact, yeah, I have. With my classes, my AP physics class in McMinnville, we built a big one as a class project. I mean, a really big one. It was pretty cool.
My neighbor did that for his physics class.
So
What's that?
My neighbor did that for his physics
Yeah.
class in like 2008.
Yeah.
I submitted that one test, and the labels for the units question was flagged.
Oh, okay.
One that's new.
Okay.
Yes.
So this Friday, the test was going out as well.
I gotta get